Well, I was trying to give you a hint by, I was saying, we're increasing quality, what else are we increasing?
Contrast.
Huh?
Contrast?
Well,
Increasing.
here, so, we increase KV, we increase quality. What else do we increase? We increase, no, I'm going with quality here. We also, because we said it had a profound effect. it's-
Quantity.
Huh?
Quantity.
It's quantity, yes. So, remember, that when we talk about mass, we are strictly talking about quantity. And then when we talk about KV, we're talking about quality. But also quantity. Because does raising your KV increase your quantity? Profoundly, it does. That's why it has a profound effect on density. When you increase your KV, not only are you getting more energetic photons, but you're getting more of them, because didn't we say when you increase KV, you increase the efficiency of the process of producing X-rays? At low KV, we might produce 0.5% of the beam of photons, but at a high KV, it could be double that, which is a huge amount. It goes up to 1%. So KVP, yes, we associate it with quality, but it also has an impact, a big impact on quantity. You gotta remember that KV is both quantity and quality. Quality first, but also remember that it's quantity. And then mass is only quantity. And you were right, mass is with density, and KVP is the controlling factor of contrast, right? If you wanted to change your contrast, you wouldn't change your mass. And if you wanted to change your density, but you didn't want to change your contrast, then you would change your mass, right? Because each of them are the controlling factors, even if KVP has a profound effect on density. So you would only change your KV if you really wanted to change your contrast. Yeah. When we have a problem, when I give you a problem where you have to apply the inverse square law, what kind of units would you expect to see? Rankins. Rankins or millirankins, yes. What is the Rankine? What, someone define the Rankine. The Rankine is a unit that we could say of exposure or intensity, but it's actually a measurement of ionizations in air, right? So when we're talking about what the dose the patient's getting, yes. When we're measuring it for the inverse square law, we're talking in Rankines. It's actually not, we're not getting into the real difference, but there are about 5 different units and they mean different things. A Rankine is ionizations in air. A REM is the amount of radiation that you absorb multiplied by a weighting factor. If you absorbed it here, it would be a weighting factor for the chest. If it was in your gonads, it would be a much higher weighting factor because it's more damage, right? If it's in the eyes, it's going to be a higher weighting factor. So that's REM. Then we have grays or RADS. That's just radiation absorbed. It doesn't really tell us how dangerous it is. It just said she absorbed 10 RADS. If we wanted to know how dangerous it was, the biological effect, it would be in REM then. Yeah? So Rankine is when we are doing these applications of the inverse square law. They are an intensity or just the best way to just say it is exposure. Okay. Oh, binding shells. Binding shells, the binding energy. Where would you expect to see the highest amount of binding energy in an atom? What shell?
K-shell.
A K shell. Where would you expect to see just an electron itself that had more energy? which shell would you expect to see then?
Outer shell.
The outer shell, right? Tell me, under what circumstances would you say that the inner shell electron was really tightly bound? I mean, they're all tightly bound, but which type of atom would you say it's really tightly bound?
High Z number?
A high Z number. More shells, more electrons. The more shells you have, the tighter it is in the center, right? Definitely be able to explain the photoelectric absorption, that interaction, and the Compton interaction, because there'll be questions where you'll have to apply that information. You gotta know the differences between them. Photoelectric, inner shell, ionization, and it's the inner shell electron that gets knocked out. Compton, ionization, it's the outer shell electron that gets knocked out. We know the difference between the two of them. When we have a photoelectric interaction, we get secondary radiation. Can someone explain that? Secondary or characteristic radiation? What happens?
Yeah, that's scatter, but that's the resulting energy.
It's not scatter.
It's the resulting energy from interaction between.
You'll do better than that. Go ahead.
It's the photon released from the cascade effect from the outer shell electrons.
Right, so when you knock out that inner shell electron, outer shell electrons do a cascade and keep on dropping down because the atom wants its inner shells filled until the vacancy. It drops all the electrons down to the vacancy is now in the outer shell. That's the only way that the atom feels the best is if there's if it has to have a vacancy, if it's on the outer shell. So as they drop down, there's a difference between the binding energies of each shell, and as they drop down, that difference in binding energy comes out as a secondary photon. It's not a scattered photon, it's what's left over in that cascade that comes out. And this happens also in the tube, and since the anode is tungsten, we know the difference between the K and L shell, that it releases a photon worth about 69.5 keV, which becomes part of the beam. It's a useful part of the beam. So it's not scatter, it's a result of this cascade.
Can they interact with the IR?
Yes.
The secondary radiation, but we differentiate between that and the scatter?
The scatter is what's left over after a Compton interaction and gets scattered in a different direction. So in the Compton interaction, we knock out an outer shell. Not all of the photon's energy was used to knock it out. Whatever's left over comes out, boom, as a scattered photon. What's ever left over, right? That's the outer shell. This is when we knock an electron out of the inner shell in a photoelectric interaction. The next electron has to drop down to fill that hole. The differences between the two shells' binding energy is the energy that's left over, and that's not from the original photon. It's left over from changing and filling these vacancies. That comes out as a secondary photon as part of the beam. And if it's from tungsten, then we know at 69 kV it's a useful photon that can actually go through the patient and hit the IR and carry information, right? But with scatter, there is no useful information. It's just leftover energy from a Compton interaction that just shoots out in a different direction. We don't get a dose from characteristic radiation. That's absorbed by the patient or makes it to the IR. We do get our dose from scattered from Compton because it comes flying out in a different direction. Yeah. Okay. So, let's stick on this idea of secondary radiation. I kind of already said, when it hits the anode, which is made of tungsten, that gives us a useful photon. If I were to give you all different elements and ask you if there was a photoelectric effect that resulted in secondary radiation from any of these different elements, which element would you choose that would be the most useful for us?
Lead, that's asking, off.
What?
Lead, that's asking.
No, you're off on
Is
that one.
that barium, iodine? Those
Yeah.
process stages?
Well, what we'd be doing is, we'd be looking at the element that has the highest Z number. Because if it has a low Z number, it's gonna have very few electrons with very low binding energy, so anything that comes out of that characteristic cascade is useless, it's just reabsorbed and it doesn't add to our image. That's why we use tungsten, because the secondary radiation from tungsten is 69.5 keV. It's a useful photon. So if an element has a low Z number, it's sort of useless to us because the amount of radiation that comes out as secondary radiation is just absorbed. Yeah. Someone explain Compton interaction. Compton interaction. What is a go ahead.
Interaction with the outer electron shell, or like the outer shell, electron, so it just knocks it off.
So Compton ionizes the atom by knocking out an outer shell electron. And what was photoelectric?
Inner shell.
So it's ionization. What's ionization mean?
Knocking out electron.
There was enough energy to eject electron, right? And it only happens for us in these two interactions. So on the photoelectric, it knocks out the inner shell, and that photon energy is completely absorbed, which is the patient's dose. On Compton is only partially on the outer shell. It ejects it, so it ionizes the atom. Ionizing, meaning it has a charge now, right? And that leftover energy pops out as a secondary photon, right? A scattered photon. Make sure you know the definition of pair production and of photodisintegration. If we were comparing interactions to contrast, could someone do that? Tell me what interactions we see when we see certain types of contrast.
PE. See photoelectric with varying degrees of density.
So photoelectric gives you what type of contrast? Use the words that we use to describe contrast. Short scale. Right? And what else is another way to say short scale? High contrast. I think we'll just stick with those two right now, that short scale contrast, black and white, more black and white, is the same as high contrast. Yes? Long scale contrast, many shades of gray, is low contrast. Gotta remember these, because when we hit contrast in about 3 or 4 weeks, then you're gonna have 12 words to explain contrast.
So PE is short scale contrast.
Correct. Yes.
So would Compton be long?
Say again?
So would Compton be long scale?
Yes. And Compton is long or low contrast, many shades of gray, higher KV. You're gonna come up, when we finally hit contrast, one of your assignments is to come up with an acronym or a saying or something or other where you use all the words that describe the contrast. And this way you will remember. What generally happens is that